Welcome to the deep dive. Today we're cracking open the history of something probably inside the device you're listening on right now, but maybe don't think about too much the Intel desktop processor.
Yeah, it's a fascinating journey. We've dug through a whole lot of sources to map this out.
Exactly. You asked us to explore how these chips evolved, so that's the plan. We're not just listing model numbers, though.
No way. We want to get into, the key moments, the big architectural shifts, the rivalries.
Right, the stuff that really shaped Intel's massive impact on desktop computing. Hopefully, by the end, you'll have a much better feel for how your computer actually got its brain.
And it's funny because Intel, this, processor giant, they didn't even start there.
Right. Back in '68, when Robert Noyce and Gordon Moore founded it, they were all about memory.
Yeah, SRAM, DRAM. Remember the 1103 DRAM chip? That was big for them, and EEPROM, stuff like that. Memory was their game.
But then they got this kind of side quest, didn't they?
Exactly. In 1969, this Japanese company, Busicom, came calling. They needed 12 custom chips for a calculator.
A calculator. And one Intel engineer, Ted Hoff, had a totally different idea.
Yeah, instead of 12 specialized chips, he was like, hang on, what if we make just 4 chips, but one of them is a general purpose processor you can program?
And boom, 1971, the Intel 4004 arrives.
The 4004, that was it. The first commercial single chip microprocessor. The whole CPU right there on one tiny slice of silicon.
Wow. How powerful was it back then? Specs must seem tiny now.
Oh, totally tiny. About 2,300 transistors, ran up to maybe 740 kilohertz.
Okay.
But here's the kicker. Its computing power was actually comparable to the ENIAC. That massive room-sized computer from the 40s.
Get out of here. That's incredible. So it wasn't just a chip. It was a whole new way of thinking.
Exactly. It shifted everything from custom, single-purpose chips to this programmable building block idea.
Yeah.
Intel saw the potential, got the rights back from Busicom, and started marketing it everywhere. Smart move.
And they didn't waste time. A year later, 72, we get the 808.
Yep, 8-bit this time. Twice as powerful as the 4004. Started showing up in some early computer-like devices.
But 74 was the real ignition point, wasn't it? The 8080.
Oh, yeah. The 8080 was a major upgrade, designed for, a much wider range of uses, about 4,500, maybe 6,000 transistors, running at 2 megahertz.
And that chip ended up in something pretty legendary.
The MITES Altair 8800. The 8080 was basically the brain of the machine that arguably kicked off the whole personal computer revolution.
It's amazing how that partnership worked out. The Altair got way more popular than anyone expected, right? Selling thousands of kits.
Tens of thousands. And suddenly, there's this huge demand for the 8080. It really put Intel's 80 series chips on the map.
But it wasn't just Intel, right? That early microprocessor scene was pretty wild.
Oh, definitely competitive. You had Texas Instruments with their TMS 1000 in 74.
Oh.
That was interesting because it put the CPU, RAM, ROM, I/O, everything on one chip. Ended up in calculators, watches, that sort of thing.
Okay.
Then Motorola jumped in with the 6800, another 8-bitter, also 74.
And the company that powered Apple IIs and Commodore.
MOS technology. Yeah, founded by some ex-Motorola guys. They came out with the 6502 and 75.
That chip was everywhere.
Hugely successful. Apple II, Commodore PET, the C64, Atari consoles. It was efficient, good performance, even at lower clock speeds. And crucially, it was cheap to make.
And cost was definitely a factor. What about Zilog?
Right, Zilog. Also founded by ex-Intel engineers, guys who'd worked on the 4004 and 8080. They launched the Z80 in 76.
And the Z80 had a clever trick up its sleeve.
It did. It was software compatible with the Intel 8080. So programs for the 8080 could often run on the Z80, no changes needed. Plus, it had extra features and was often cheaper.
Smart. So it became a popular alternative.
Hugely popular. Powered tons of computers in the late 70s, early 80s. Even consoles like the original Game Boy and Sega Master System used it later on.
It really shows, doesn't it? It wasn't always just about the fastest tech.
Not at all. Cost, compatibility, getting those early design wins in popular systems, that was absolutely key back then.
So as the 70s wore on, 8-bit was starting to feel a bit limited?
Yeah, definitely. Memory was getting cheaper, software more complex. People needed more power, more memory address space. The industry was shifting towards 16-bit.
And Intel saw this coming, with competition like Motorola and Zilog working on 16-bit chips.
Right. Intel actually had this super ambitious 32-bit project, the IAPX 432. But it was, let's just say it was delayed a lot.
So they needed something sooner.
Exactly. So they developed the 8086 as kind of an interim step, but wow, did it turn out to be strategic.
Launched in '78, Intel's first 16-bit microprocessor, big step up.
Huge. 16-bit talking to the outside world, and it had this 20-bit address bus.
How did they manage 20 bits with 16-bit registers?
Through memory segmentation. Think of it like having different memory banks or segments it could point to. That let it address up to 1 megabyte of memory.
Which was massive compared to the 64 KB limit of most 8-bit chips.
Massive jump. It packed about 29,000 transistors, started at 5 megahertz, went up to 10 megahertz later. But the really huge thing, the lasting legacy, was the x86 instruction set architecture, the ISA.
The language the processor understands. And that's still with us today, fundamentally.
Pretty much. It's been extended like crazy over the decades. But that core x86 ISA started right there with the 8086.
But getting it adopted wasn't automatic, right? Yeah. Especially with chips like the Motorola 68000 around, which some people thought was technically better.
True. So Intel launched Operation Crush around 7980, massive marketing push, ads, developer support, deals for manufacturers. They went all out to get design wins for the 8086.
And it worked.
It really did. Secured thousands of wins, cemented the 8086 in that 16-bit market. It shows good tech needs good strategy, too.
Then came a variation, the 8088 and 79. What was the difference there?
Okay, so internally, pretty much the same as the 8086. 16-bit core, 1 MB memory addressing. The key difference was the external data bus. It was only 8 bits wide, not 16.
Seems like a step back. Why do that?
Cost.
Yeah.
When IBM was cooking up their first PC, they wanted 16-bit power, but needed to keep it affordable and use existing, cheaper 8-bit components.
Ah, I see. So IBM looked at the 8086, the 8088, and the Motorola 68000.
Yep. The 68000 was powerful, but IBM knew Intel had tools, Microsoft had BASIC ready for the 808, 688, and that 8-bit bus on the 8088 meant IBM could use cheaper support chips, less RAM, simpler motherboard design. Saved a lot of money.
And Intel gave them a good deal on the 8088, too.
Better price, better availability at the time. So IBM chose the 8088.
And the IBM PC, launched in 81, was just massive.
Absolutely colossal success. Way bigger than even IBM expected. And suddenly the whole industry starts building PC compatibles, all based around that Intel 8088 and its x86 architecture.
So that cost-saving measure, the 8-bit bus, basically locked in x86 for decades.
Wow. It's fascinating, isn't it? Sometimes a practical choice has the biggest long-term impact.
So after the 8086 and 8088 set the stage, Intel kept evolving x86 through the 80s.
Yeah, they didn't stand still. In 82, you got the 8186 and 8188. They integrated some extra bits like timers and interrupt controllers onto the chip. More for embedded systems, though, not so much desktops.
Okay, but then came a big one, the 286.
The 80286, also 82. That was a significant upgrade. Introduced protected mode.
What did protected mode allow?
Access to way more memory, up to 16 megabytes. And hardware support for multitasking. That chip powered the IBM PC-AT, which was a really influential machine.
And then the jump to 32-bit?
The 80386 in 1985, a true landmark.
Mm-hmm.
Full 32-bit registers could directly address 4 gigabytes of memory, plus paged memory management, which was critical for modern operating systems like Windows and OS2.
And Compaq actually beat IBM to market with the 386 machine?
They did. Compaq Despro 386 in 86 kind of signaled a shift that IBM wasn't the only leader anymore.
Then rounding out the 80s, the 486 in 89.
Right, the Ada 486, another big performance jump. Key things here, we're integrating the math coprocessor, the floating point unit or FPU, right onto the main chip. Before that, it was often a separate chip you had to buy. And it added a small, super-fast L1 cache directly on the die, both huge for performance.
Now, while Intel was building this x86 dynasty, the competition didn't just disappear, did it?
Not at all. Motorola's 68000 family was still going strong, powering the Mac, the Amiga platforms known for their graphics.
Right, different ecosystems.
And importantly, AMD started becoming a direct x86 rival. They'd been a second source for Intel chips earlier, but after some legal tussles, they started making their own compatible 386 and 486 clones.
Setting the stage for the big battles to come.
Exactly. That rivalry really started heating up then.
Which brings us nicely to the 90s and what you called the Pentium Revolution. New brand name.
Yeah, 1993, Intel launches the Pentium. They decided, let's move past these numbers, let's build a brand. But it wasn't just marketing. The P5 microarchitecture inside was a big deal.
How so? What made it different?
It was superscalar. Basically, it could start working on more than one instruction at the same time, like having 2 parallel processing pipelines instead of just one. Big performance boost.
Okay.
It also had a wider 64-bit external bus to talk to memory faster, and separate L1 caches for instructions and data, which was more efficient.
So Pentium really became the standard for PCs in the 90s, made things like Windows 95 possible.
Pretty much. It powered that whole multimedia boom. But it wasn't all smooth sailing. Remember the FDIV bug?
Oh, yeah, the floating point division error in '94. That caused a bit of a stir.
It did. Intel's initial handling wasn't great, but they eventually did a massive recall and replacement program. Then focus shifted more to multimedia.
MMX, Pentium MMX, late 96, early 97.
Right. MMX added these special SIMD instructions. Single instruction, multiple data. Basically, ways to speed up audio-video graphics processing really significantly.
And even before MMX, there was a high-end chip, the Pentium Pro.
Yeah, late 95. Pentium Pro was aimed squarely at servers and workstations, introduced the totally new P6 microarchitecture. This was a really advanced design for its time.
What made the P6 architecture special?
Out-of-order execution was a big one. The chip could intelligently reorder instructions to keep its execution units busy, even if the program code wasn't perfectly optimized. In super pipelining, breaking instructions into even more, smaller steps to let the clock speed run higher. Plus, it uniquely had the L2 cache built right into the same package as the CPU core, which was very fast but also expensive.
So, too expensive for regular desktops.
Generally, yeah. So Intel needed a way to bring that P6 goodness to the masses.
Enter the Pentium 2 in 97.
Exactly. Pentium 2 took the P6 core, added MMX, but put it on this new Slot 1 cartridge. The L2 cache was on the cartridge too, but as separate chips, running at half the core speed usually, made it much cheaper to produce.
Okay, so Slot 1 was a cost-saving measure for the cache.
Pretty much. And then for the budget end, they launched Celeron in 98.
Celeron. That name stuck around for a long time. How was the first one?
The very first Celerons were not great. Basically a Pentium 2 with the L2 cache completely disabled. Slow.
Ouch.
But the second version, the Celeron 300A, based on the Mendocino core, that one had L2 cache integrated right onto the die, just smaller than the PIIs.
Yeah.
It was fantastic value and became legendary for overclocking. People love that chip.
The Mendocino Celeron. I remember that. And
Yeah.
then the Pentium III arrived in 99.
Yeah, Pentium III. Still based on the P6 architecture, but its main new feature was SSE streaming SIMD extensions.
More multimedia instructions?
Kinda. SSE was focused more on floating point calculations and 3D graphics, stuff becoming really important for games.
And the PII had a few versions too, right? Slot 1, then sockets.
Yeah, it evolved. Started with Katmai on Slot 1 with that off-die L2 cache. Then came Coppermine, which was a big step, moved to socket 370, put the L2 cache back on the CPU die, running at full speed, big performance boost, and later Tualatin, another refinement on socket 370, often with more cache.
But while Intel was doing all this P6 evolution, AMD was really starting to make waves.
Oh, absolutely critical context for the late 90s. AMD wasn't just cloning anymore. Their K6, K6-2, K6C3 processors were seriously competitive, especially on price performance. They kept the older Socket 7 platform alive with Super Socket 7, adding faster bus speeds.
Gave people an upgrade path without needing a whole new Intel motherboard.
Exactly. But the real earthquake was the AMD Athlon in mid-1999.
The K7 architecture.
Completely new design, very powerful. Used its own slot initially, slot A. Looked like Intel's slot 1 but wasn't compatible. And the Athlon was fast. Really fast. Often beat the Pentium III clock for clock.
And AMD beat Intel to 1 gigahertz.
They did. That was huge bragging rights. That competition, especially from Athlon, was intense. It really spurred Intel on. The quick launch of the Coppermine P5 with its on-die cache, probably a direct response to Athlon breathing down their necks.
That fierce rivalry was well and truly underway.
Absolutely. And it set the stage for the next chapter, the NetBurst era.
Ah, yes. The early 2000s.
Yeah.
All about clock speed, right. The Pentium 4.
That was the goal. Launched in 2000, the Pentium 4 debuted the brand new NetBurst microarchitecture, and the philosophy was radically different.
Yeah.
Designed for frequency, aim high, like 10 gigahertz eventually was the dream.
10 gigahertz. Wow. How did they plan to get there?
Key thing was hyperpipeline technology. Very, very long instruction pipelines. Think like a super long assembly line. Many, many stages.
Okay. What's the benefit of a long pipeline?
In theory, you can crank the clock speed higher because each stage does less work. But the downside is, if the chip guesses wrong about what instruction comes next, a branch misprediction, you have to flush that whole long pipe and start over. Big penalty.
Ah, I see. Trade-offs.
Definitely. They also had a rapid execution engine where some core parts ran at double speed and an execution trace cache instead of a traditional L1 instruction cache, and a quad-pumped front-side bus to get data in and out faster. Plus, new instructions like SSE2.
So did the first Pentium 4 live up to the hype, the Willamette core?
Honestly, Not really. Especially at lower clock speeds, it often lost to the older high-end Pentium IIIs in many common tasks. It needed high clock speeds just to pull even.
Not a great start. Did it get better?
It did. The Northwood core was much more successful. Double the L2 cache, ran faster, and crucially, introduced hyper-threading on some models.
Hyperthreading, making one core look like two to the operating system.
Exactly. Great for multitasking, helped keep that long pipeline fed. Northwood P4s were pretty popular.
What came after Northwood?
Prescott. Pushed clock speeds even higher, added SSE3, but Prescott ran hot, really hot, and used a ton of power. They basically hit a thermal wall.
Yeah.
It became incredibly difficult to cool, and power chips running much faster. The 10 gigahertz dream died there.
Ouch. So they couldn't just keep cranking the clock speed.
Nope. The last single-core net burst was Cedar Mill, which was basically Prescott shrunk down to a smaller manufacturing process. Helped with power a bit, but the architecture had hit its limit.
And during this time, AMD was still pushing hard, right? And moving to dual-core.
Oh, yeah. AMD's Athlon 64 X2 dual-core chips were out and performing really well. Intel needed an answer, and their first shot was the Pentium D in 2005.
Pentium D, Intel's first dual-core desktop chip. Was it a clean design?
Not really. It was basically two single-core Pentium 4, Prescott or Cedar Mill, dies slapped together on one package. Not an integrated dual-core design like AMD's.
So it inherited the heat and power issues.
Pretty much, yeah. Often ran very hot, used a lot of power, and wasn't always faster than AMD's dual cores, especially per watt. It was kind of a stopgap measure. This era also saw socket changes. 423, then 478, then the move to LGA 775 land grid array, pins on the motherboard.
So while Intel was wrestling with net burst limits, AMD was having a pretty good run.
You could call it AMD's golden age, for sure. Their Athlon XP kept pace well with the P4, but the Athlon 64 in 2003, that was huge.
64-bit computing for the desktop?
Yep, AMD 64 architecture.
Yeah.
And maybe even more importantly, they integrated the memory controller directly onto the CPU die.
Why was that such a big deal?
Lower latency. Data didn't have to go across the slower front-side bus to a separate chip on the motherboard to reach RAM. It made memory access much faster. Think shorter commute time for data.
Gotcha. Big performance win.
Huge. And their dual-core Athlon 64 X2 in 2005 built on that. Widely seen as superior to the Pentium D, faster in many cases, much more power efficient. AMD gained a lot of market share and respect during this time.
So Intel realized net burst wasn't the future. They needed a change in direction.
A major change. They basically admitted defeat on the frequency is everything path and went back to the drawing board, focusing on efficiency performance per watt.
Where did they look for inspiration?
Back to their own successful mobile chip, the Pentium M, which, interestingly, had roots in the older, more efficient P6 architecture that powered the Pentium Pro, PII, and PISIC. It was kind of a return to those principles.
So learning from the past to build the future.
Exactly. This led to the development of the Core microarchitecture, launched in 2006. The goal was clear. High performance, low power consumption. A total pivot.
What were the key features of this new Core architecture?
Shorter, wider pipeline compared to NetBurst. Could do more work per clock cycle with less penalty for errors. Shared L2 cache between the cores for better data sharing in dual-core chips. Smarter memory access, faster SSE execution, much better power management.
And they dropped hyperthreading initially.
Yeah, the first Core 2 chips didn't have it. They felt the core itself was efficient enough.
So the first chips using this were branded Core 2.
Yep, Core 2 Duo for dual core. Codenames like Conroe, Leader Wolfdale, and Core 2 Quad for quad core. Kentsfield, Yorkfield, often two Duo dies together. Launched mid-2006.
And how were they received? Did they turn things around for Intel?
Instantly. Core 2 absolutely blew NetBurst away in performance and efficiency. Intel basically reclaimed the performance crown overnight. It was a massive comeback. They also had Extreme Edition versions for enthusiasts unlocked for overclocking.
Wow. So Core architecture was a huge success. What came next? The I-Series.
Right. Building on that success, Intel launched the first Core I-Series processors in late 2008. This was the Nehalem microarchitecture, another big step.
What did Nehalem bring to the table?
Integrated memory controller. Finally matching AMD there, bringing those latency benefits. Hyperthreading made its return.
Okay, good to see that back.
Turbo Boost technology debuted, letting the chip automatically clock higher when conditions allowed, and they replaced the old frontside bus with QPI, Quick Path Interconnect, on high-end chips and DMI, Direct Media Interface, on mainstream ones. plus a shared L3 cache. It was a much more modern modular design.
And this is when the Tick-Tock strategy started.
Exactly. After Nehalem, Intel settled into this really predictable rhythm. TIC was shrinking the existing architecture to a smaller manufacturing process, like going from 45 millimeters to 32 millimeters. Focus on efficiency, smaller size.
Yeah.
TOC was introducing a brand new microarchitecture on the current process. Focus on performance, new features.
Gave consumers and the industry a clear roadmap.
Totally. So Sandy Bridge in 2011 was a TOC on 32 nanometer. Big one. Introduced the ring interconnect, graphics on the die, AVX instructions. Huge performance jump again.
Then Ivy Bridge in 2012 must have been the TIC.
Yep. TIC down to 22 millimeter. Introduced their Tri-Gate 3D transistors. Better integrated graphics, PCIe 3.0 support.
Haswell in 2013.
TOC on 22 millimeters. Big focus on power efficiency, especially for laptops. Introduced i5VR, fully integrated voltage regulator. AVX2 instructions.
Broadwell.
TIC to 14 millimeter. Mostly 2015, but this is where Tick-Tock started to wobble.
Mm.
Broadwell desktop launch was very limited, late, mostly mobile.
The first signs of trouble with the process shrinks.
Yeah. Then Skylake in 2015 was the TOC on 14 millimeter. New architecture, DDR4 memory support, lots of platform updates. Skylake is a really solid foundation.
Now, during this whole Core and Tick-Tock dominance by Intel, what was AMD up to? Were they keeping pace?
Honestly, it was a tough period for AMD. Their Phenom and Phenom Techie chips offered decent multi-core value, but after Nehalem, they really struggled to match Intel's single-thread performance and efficiency.
And then came Bulldozer.
Yeah. AMD's FX processors, based on the Bulldozer architecture, launched 2011. The design was ambitious, focused on multi-threading with paired modules, but it just didn't deliver in most real-world scenarios, especially single-threaded tasks in gaming. Power consumption was also high. Intel really pulled ahead during this time.
So Intel was dominating, but then the Tick-Tock model started to break down.
Yeah, the late 2010s onwards. Moving beyond 14 millimeter proved much, much harder than Intel expected. Huge delays. So Tick-Tock kind of died, replaced by, well, more 14 millimeter.
So we got several generations just refining 14 millimeter.
Pretty much. Kaby Lake 7th gen was basically an optimized Skylake. Then Coffee Lake 8th gen was a bigger step. Intel finally started adding more cores to mainstream chips, largely in response to AMD's comeback.
Ryzen. We'll get to that. So Coffee Lake brought 6 cores to the mainstream i5, i7.
Yep. And Coffee Lake Refresh, 9th gen, pushed that to 8 cores for the i7, i9. Still on 14 millimeter, but with more cores to compete. They added a bunch of plus signs to the 14 millimeter name, plus.
Meanwhile, 10 millimeter process was struggling.
Big time. Cannon Lake was the first 10 millimeter chip, but barely launched, mostly just one laptop model, very low volume. Ice Lake 10th Gen Mobile was the first real 10 millimeter volume product in 2019. New Sunny Cove cores, much better integrated graphics, but still no 10 millimeter for desktop yet.
So what did desktop get for 10th Gen?
Comet Lake in 2020. Still 14 millimeter plus, pushed core counts again of 10 cores on the i9, also brought hyper-threading back to the i3 and i5 lineups.
Okay, still squeezing performance out of 14 millimeter. What about 11th Gen desktop?
Rocket Lake in 2021. This was weird. They actually took the 10 millimeter Sunny Cove core design from Ice Lake Mobile and backported it to run on the 14 millimeter process. They call the core Cypress Cove.
Backported? Why do that?
To get the IPC instructions per clock improvements of the newer core design onto desktop faster, since 10 millimeter desktop wasn't ready. It worked. IPC went up significantly. But because the cores were bigger, they had to reduce the max core count back down to 8 on the i9. It did add PCIe 4.0 and new Xe graphics, though.
Quite a convoluted path, but then came a real architectural revolution.
Alder Lake, late 2021.
Yeah.
12th generation. This is the big one.
Yeah.
Built on Intel 7 process, what they used to call 10 millimeter enhanced SuperFin. And it introduced the hybrid architecture.
P cores and E cores. Performance cores and efficient cores.
Exactly. Big, powerful P cores, Golden Cove design for demanding tasks, and smaller, low-power E cores, Gracemont design, for background stuff and boosting multi-threaded throughput.
How did the system know which core to use?
Intel Thread Director, hardware built into the CPU that gives hints to the operating system, Windows 11 specifically was optimized for it, to schedule tasks intelligently onto the right type of core.
Clever stuff. And Alder Lake brought other new tech, too.
Yeah, DDR5 memory support, PCIe 5.0 support, new LGA 1700 socket. Alder Lake was a huge step up and made Intel really competitive again, especially at the high end.
And they've refined that hybrid model since.
Yep. Raptor Lake, 13th gen, in 2022, kept the same P cores, but doubled the number of E cores on many models. increased cache sizes, pushed clock speeds higher, solid improvement.
And 14th gen.
Raptor Lake refresh in late 2023.
Mostly just slightly higher clock speeds again, maybe some minor feature tweaks. Still on Intel 7, still LGA 1700, more of an iteration.
Okay, so what's next? We're hearing Core Ultra. Right. New branding, new architecture direction, starting with Meteor Lake for laptops late 2023. This is where Intel fully embraces chiplets, or tiles as they call them.
So the CPU isn't one piece of silicon anymore.
Nope. Meteor Lake uses multiple tiles connected with their Foveros 3D packaging. There's a compute tile with the new P-cores, Redwood Cove, and E-cores, Crestmont, made on Intel's new Intel 4 process. Then there's a separate GPU tile using their Arc Graphics tech made by TSMC. And SoC tile with very low-power E-cores and the new NPU neural processing unit for AI tasks, and an I/O tile.
Wow, breaking it all apart. More flexibility.
That's the idea. Use the best process node for each job. Mix and match. And that dedicated NPU for AI is a big new focus.
And this tile approach is coming to desktop, too.
Expected with Arrow Lake probably later in 2024. Also branded Core Ultra. Rumored to use even newer Lion Cove P-cores and SkyMont E-cores, possibly made on an even newer process from TSMC, likely a new socket, LGA 1851, and expected to include an NPU too. One interesting rumor is it might drop hyper-threading on the P-cores.
Interesting. But throughout this recent period, Intel hasn't been operating in a vacuum. AMD made a huge comeback.
Absolutely massive. Ryzen, launched in 2017 based on the Zen architecture, completely changed the game. High core counts, really strong multi-threaded performance, competitive single-thread performance, thanks to big IPC gains.
Then they used chiplets too, right?
Yeah, from Zen 2 onwards. They beat Intel to market with that for mainstream desktop. Allow them to scale core counts effectively and keep costs reasonable. Successive Zen generations just kept improving. Zen 3 was a big leap. Zen 4 brought DDR5 and PCI 5.0.
And those X3D chips for gaming?
Right, adding huge amounts of L3 cache using their 3D V-cache stacking technology. Made a massive difference in many games. AMD has been consistently competitive, often leading in multi-core, sometimes in gaming. They really forced Intel to ditch the complacency of the late 14nm era and innovate aggressively with things like Alder Lake.
It really has been an amazing back and forth. Looking back from that simple 4004 to these complex, tiled, hybrid, AI-boosted processors, it's just incredible.
It really is. That constant push for performance, first through raw clock speed, then efficiency, now heterogeneous cores and specialized units, manufacturing getting ever smaller, now breaking chips apart into tiles. Wild ride.
So what are the big takeaways for people listening?
Well, first, the x86 architecture born with the 8086, its legacy is just immense, still dominates desktops and servers. Second, Moore's Law drove things for decades, but it's really hit challenges recently, forcing new kinds of innovation beyond just shrinking transistors.
Right.
Third, competition is crucial. That Intel-AMD rivalry, especially the Ryzen resurgence, has pushed innovation way harder than when one company was totally dominant. Fourth, the shift to hybrid architectures, P-cores, E-cores, and specialized units like NPUs for AI. That seems like the clear direction forward.
Makes sense. Combine different strengths.
And finally, that move to disaggregated tile-based designs. That offers huge flexibility. It might be key to pushing performance further when shrinking single chips gets harder and harder.
So a final thought to leave people with. We've got these hybrid CPUs, dedicated AI hardware is popping up everywhere. ARM chips are making serious inroads into PCs. What does the next decade look like?
That's the big question, isn't it? Will the traditional CPU as we know it fundamentally change even more? How much processing will shift to specialized units like NPUs or even GPUs? And how will that change the computers we use every day?
Lots to think about. The silicon world definitely doesn't stand still. Thanks for diving deep with us today on this amazing history.